summer school online program on smart city. Today I'm the moderator for this upcoming lecture. First of all, let me introduce our speaker for this upcoming lecture, Dr. Mohammed Ramzan, who is a senior mathematician at Antibacterial University in Islamabad in Pakistan. He has published around 125 ISI indexed papers in renowned international journals. At present, 4 PhD and 3 master students are working in his lab. 14 master students have successfully completed their research work with him. He has received Best Paper and Best Presenter awards in Antalya, Turkey in 2018 and Kuala Lumpur, Malaysia in 2017, respectively. He was also visiting professor at Jiangsu University in China and Sejong University in Korea. He has also received of different projects in the PI and co-PI position. Let's welcome Dr. Mohammed Ramzan, and thank you again in advance for your lecture.
Can I start now?
Yeah, Dr. Mohammed, you can go ahead.
Okay. Thank you very much for inviting me to present my work to this summer consortium. I'm also presents my thanks to the chair, the summer consortium's head. It certainly be a great platform for sharing knowledge and information in the form of a variety of illustrations. This will certainly be helpful to the students who are looking for a path for their future goals. I'm also thankful to Dr. Yan Zheng, Dr. Yu Bei, Dr. Liu, and of course Dr. Lin Liu for providing this platform to share my knowledge. Now, let me share my presentations with you. Now, what is nanofluids? Nanofluids are a new class of nanotechnology-based heat transfer fluids obtained by dispersing the stably suspended nanoparticles, typical dimensions on the order of 10 nanometer size. Why nanofluids? The goal of nanofluids is to achieve the highest possible thermal properties at the smallest possible concentrations, preferably less than 1% by volume, by uniform dispersion and stable suspension of nanoparticles, preferably less than 10 nanometer size in most fluids. To achieve this goal, it is vital to understand how nanoparticles enhance energy transport in liquids. If we talk about the range of applications, nanofluids have great potential in transportation to improve automotive and heavy-duty engine cooling rates by increasing the efficiency, lowering the weight, and reducing the complexity of the thermal management system. According to different researches, the application of nanofluids in industrial cooling will result in great energy savings and emissions reductions. For the United States industry, the replacement of cooling and heating water with nanofluids had potential to conserve 1 billion BTU of energy. Moreover, magnetic fluids are kinds of special nanofluids which take advantage of magnetic properties of nanoparticles inside. For example, the magnetic liquid rotary seals operating with no maintenance and extreme low leakage in very wide range of applications. Finally, some special kinds of nanoparticles shows antibacterial properties or drug delivery properties. So the nanofluids containing these nanoparticles may show relevant biomedical properties. If we talk about the preamble, common fluids such as water, ethylene glycol, and oil play an important role in heat transfer in many industrial processes such as power generators, heating or cooling processes, chemical processes, and microelectronics. These fluids have a relatively low thermal conductivity and thus cannot reach high heat exchange rates in thermal engineering devices. A way to overcome this barrier is using ultrafine solid particles suspended in common fluids to improve their thermal conductivity. The suspension of nano-sized particles with a size 1 to 100 nanometer in conventional based fluids is called the nano. Choi first used the term nanofluid in 1995. Nanofluid compared to suspensions with particles of millimeters or micrometers size show better stability, rheological properties, and considerably higher thermal conductivity. The enhanced thermal behavior of nanofluids would provide a basis for numerous innovations for heat transfer intensification, which is of great importance to the number of industrial sectors, including transportation, power generation, micro manufacturing, thermal therapy of cancer treatment, chemical and metallurgical sectors, as well as the heating, cooling, ventilation, and air conditioning. Nanofluids now coming to the layout of the presentation, this will comprise the definition of the fluids, properties of the fluids, which can consist of, let's say, the thermal conductivity, the viscosity, then the different thermal conductivities of the different fluids, timeline of convergence of nanofluids, types of nanoparticles, types of nanofluids, feature of nanoparticles, long-term stable nanofluids, overview of some experimental results, effects of some parameters on thermal conductivity of nanofluids, mechanism of heat transfer in nanofluids, application of nanofluids, challenges in nanofluids, research opportunities in nanofluids, and finally the references. Now, first, what is a fluid? Fluid basically is a substance that is capable of flowing It is a substance that is capable of flowing It has no definite shape of its own. Both liquids and gases are fluids. Example of fluids are water, milk, petrol, honey, air. If we talk about the properties of the fluids, the first one is the viscosity. Viscosity is defined as the resistance of a fluid to the flow. It often refers to the thickness of the fluid, the state of being thick and sticky due to the internal friction cooling the fluid raises its viscosity. Now coming to the density. The density of a substance is the relationship between the mass of the substance and how much space it takes up, means the volume. Fluids that do not mix layer themselves according to their density Less dense fluids float on the top of more dense fluids. An object made from the comparatively dense materials, let's say such as iron, will have less volume than the object of the equal mass from the less dense substance such as water. Now coming to the thermal conductivity. Thermal conductivity of a material describes how well the material conducts heat. To understand this, we need to learn that what is the thermal conduction. Thermal conduction is the phenomena where heat is transferred from the area of the high temperature to the area of low temperature with the motion of the constituents of a substance, such as atoms, molecules, free electrons, while the object itself does not. The thermal conductivity is the ability of a material to conduct heat. A value of the thermal conductivity can be determined by measuring the rates at which the heat can pass through a material. Thermal resistivity is the opposite of the thermal conductivity. This means not conducting much heat. Factors affecting the thermal conductivity, these include the material, the length, the temperature difference, the cross-section type. The kind of the material being used in thermal conductivity can affect the rate of energy flowing between the two regions. As far as the length is concerned, the length of the materials, the energy flow through affect the energy must flow through can affect the rate at which it flows, and obviously the temperature difference between the ends of the rods, let's say on the one side is the high temperature and the other side is the low temperature, the heat will obviously start moving from the high to the low side. And the cross-section types, obviously the bigger cross-section is there, the slow heat of rate, and if the smaller cross-section, it will be smaller heat of rate. Aqueous tends to have better thermal conductivity than gases, and solid possess better thermal conductivity than liquids. Simply we say the solids thermal conductivity is more than the liquids, and the liquid thermal conductivity is more than the gases. If we talk about the timeline of emergence of nanofluids, this basically starts in 1981. There's the tech when introduced the microchip technology. In 1985, Ergoni National Lab starts program to develop the advanced fluids. This is in USA. In 1991, Joy develops a microchannel heat exchanger in the advanced photon source at the Ergoni Lab. A funding cut for the Ergoni Advanced Fluid Program in 1992, and thereby Joy turns attention to micro, from the micro to the nano. In 1993, Mossad et al. Measured thermal conductivity and viscosity of three different water-based nanosuspensions containing aluminum oxide, titanium hydroxide, and silicon hydroxide nanoparticles with a size between 1 to 100 nanometers. They reported that both thermal conductivity and the viscosity of the water becomes greater before adding the nanoparticles. Between 94 and 97, a third proposal in 94 leads to 3 years of funding for the first nanofluids project with a focus on a proof of concept. In 1995, Joe presents a seminal paper on the concept of nanofluids at the American Society of Mechanical Engineering. Joe selected the word nanofluid for a mixture of nanoparticles and a liquid. This new class is expected to exhibit a higher thermal conductivity as compared to those of the currently used heat transfer fluids, and they represent the hope for the best enhancement heat transfer. In 1997, based on the concept of the nanofluids, Ergoni thermal scientists have developed an advanced cooling technology. The advanced cooling approach relies on many microchannels consisting of long, narrow slits only thousandths of an inch wide, and coolants containing nanometer-sized metallic particles. In other words, the innovative process employs microchannels filled with metallic nanoparticle-laden coolant to extract heat faster than the present technology. This advanced cooling approach provides more efficient cooling than any other cooling technology because the microchannels increase the effective heat transfer area and the metallic nanoparticles increase the effective thermal conductivity of the fluids. Later in 1998, Agoni Nanofluids, research funded by United States Department of Energy, and in 1999, Choi Group published the first SCI article on nanofluids, and the President Clinton in 2000 announced the United States National Nanotechnology Initiative at Caltech in January 2000. Choi serves as proposal reviewer for this talk. Choi Group published two further papers in the applied physics, and in 2002 to 3, the nanofluid work is named as the top achievement in the DY office of the basic energy sciences in both 2002 and 3. The first, in 2007, the first single scheme conference on the nanofluids was held, Nanofluid Fundamental and Applications. This was the total journey of the nanofluids from starting from the 1995 to 2007. Now, coming to the definition, nanofluids are basically an amalgamation of the nanoparticles and some basic fluids. Nanofluids are named conceived by Choi in 1905 in Anconi National Lab to describe a fluid consisting of solid nanoparticles with size less than 100 nanometers suspended in it and solid volume fraction typically less than 4%. A nanofluid basically is a fluid containing nanometer-sized particles. These fluids are engineered colloidal suspensions of the nanoparticles in a base fluids. The nanoparticles used in nanofluids are typically made of metals, oxides, carbides, or carbon nanotubes. Common base fluids include water, ethylene glycol, and oil. Now, these are some, you can say, the basics of the nanofluids. The base fluids, as I earlier told, these are the base fluids are the water, organic liquids, that's the ethylene glycol, and the oil. The size of the nanoparticles that is being inserted into the base fluids has the is 1 to 100 nanometer size, and nanometer means 10 raised power minus 9. You can imagine this size by comparing that the human hair is about 80,000 nanometer wide, and this you can say this is 10 raised power minus 9, and the human hair is 80,000 nanometer wide. A red ball cell is about 7,000 nanometer wide. You can see from this picture over here that the diameter of the soccer ball divided by the diameter of the nanoparticle is almost equal to the diameter of the Earth to the diameter of the soccer ball. So you can imagine how small this nanoparticle is. The comparison of the between two sizes of the carbon nanotubes as a typical nanoparticle with other things. You can see over here, these are the 10 millimeters, then the micrometers, and gradually it is getting down at 0.5, 0.1 nanometer size. These are the carbon nanotubes, these are the bacteria, these are the blood cells. Nanomaterials, as I earlier told, then can be the aluminum, let's say, is the oxides, there's aluminum oxide, silicon hydroxide, copper oxide, and the metals may be the copper or the aluminum, copper or the silver, and the obviously the carbon nanotubes. Now, if you compare the say the thermal conductivity, how the thermal conductivity of the base fluids these days. You can see the thermal conductivity of the fluids, the basic fluid that we use in different industrial units. The water, its thermal conductivity 0.613, similar to the glycol and the engine oil. And look at the thermal conductivity of these, let's say the metallic solids and the metallic non-metallic solids. You can see over here of the diamond is 3300, and then for the silver is 429, 401 for the copper, and 237 for the aluminum. And when these metals or the non-metallic solids are being inserted into the base fluids, the thermal conductivity of these obviously will be on the higher side. This is the same thing with the bar chart. You can compare here. These are the basic fluids. There's the water, fine glycol, and the mineral oil like this. And these are there's the copper, then the zinc, the nickel, the silicon, the ferrous, the copper oxide, zinc oxide, and so you can see the thermal conductivity as compared to the basic. The thermal conductivity of the different organic materials, heat transfer fluids, metals, and metal oxides. Therefore, by suspending metallic particles in a fluid, its thermal conductivity is expected. And similarly, this is, you can see the composition of the carbonate. This is another, you can say, the material that is used to raise the thermal conductivity of the basic fluids. These are basically the carbon nanotubes are made from the graphene sheets. Graphene has a lot promise for the additional applicants in anti-corrosion coatings and paints, efficient and precise sensors, faster and efficient electronics, flexible displays, efficient solar panel, faster DNA sequencing, drug delivery, and more. Pricing today for the graphene powder ranges from $50 to $200 per kg, depending on the quality and volume of purchase. Despite graphene being remarkably thin, it is strong enough to protect from a bullet, according to the statement described in the news. It is so thin and so lightweight that this can resist, they can protect the individual from the bullets. Carbon nanotubes basically of two types. There's the single wall carbon nanotubes and the multi-wall. If we talk about the single wall, a sheet of the graphene of one atom is in thickness is rolled in a tube. This creates a single wall carbon nanotube. The method involves combining a metal catalyst with carbon containing reaction gases, and as a result, the carbon nanotubes are formed on the catalyst within the surface. If the sheet is rolled, then we'll have single, we can say the single wall carbon nanotube, and if different shades are being rolled and overlap, then we will have the multi-wall. If we talk about the carbon nanotubes, the characteristics, these are stiff as diamonds. Diamonds is considered as the hardest, you can say, the element available in the universe. And you can see the carbon nanotubes are as stiff as the diamonds. These are 1/4 in the density of the steel, 10 times stronger than steel. The thermal capacity is 20 times more than the steel. Carbon nanotubes are elastic, are good conductor of heat. Carbon nanotubes possess good thermal conductivity, and these possess resistance to corrosion. Bicycle frames, tennis rackets, hockey sticks, bulletproof jackets. These are made from, you can say, are made from the carbon nanotubes, and you can say the experiments are on the way to use these carbon nanotubes in different products. By the use carbon tubes, weight of aircraft is reduced by 30%. Carbon tubes are used in electronic gadgets minimization. Instead of wearing vests made from the steel panels, people would start to increase their usage for the carbon fiber bulletproof vest. Carbon fiber is not only the stronger than the steel, not only stronger than steel, but it also lighter. This is because the carbon fiber is very durable and also very rugged as a material and capable of stopping bullets shot at you. The research team from the Tsinghua University in Beijing has developed a fiber that's they say it's so strong that it could even use to build an elevator to the space. They say just 1 cubic centimeter of the fiber made from the carbon tubes would not break under the weight of 160 elephants and more than 800 tons. Now, if we talk about the composition of the nanoparticles, they may be of the 0 dimension, 1 dimensional, 2 dimensional, 3 dimensional. If we talk about the 0 dimension, the length and breadth and the height is fixed as a single point. For example, the nanodots or the nanoparticles. In case of the 1 dimension nanoparticles, it can possess only one parameter, length or breadth. For example, the nanotubes, the nanorods, or nanowire. And in case of the 2 dimensional, it has two parameters, either length or breadth or height. Among these three, two can be there. For example, the nanofilms and nanocoatings. And as far as the 3 dimension nanoparticle concerned, it has the parameters such as length, breadth, and height. For example, crystals. And look at the composition, look at the figure, how you can see, let's see, these are the 0 dimension, these are the 1 dimensional, then 2 dimensional, and then the 3 dimensional. The shapes of the nanoparticles, you can see these can be the spherical, in the form of the rods, oval, cubic, triangular, star, meter, and etc. You can see the platelets, the flower, the spherical. It is observed that the platelet-shaped nanoparticles carry maximum velocity, whereas the brick-shaped nanoparticles are the best to enhance thermal conductivity. And in case of the spherical nanoparticles, good option for the drug. Here, this is the preparation. Now, if we come to the preparation for the nanofluids, this is the zinc oxide in water that is produced with two-step method, and copper nanoparticles in cycle are produced in one-step. Now, the nanoparticles can be, you can say, be produced by two methods. One is named as a one-step, and the other one is two-step. It should be kept in mind that the nanofluids are prepared simply, it's not prepared simply by adding the nanoparticles to water or oil and stirring the mixture. Similarly, we mix the sugar with tea, but rather the formation of nanofluids requires special physical and chemical processes in order to produce a uniform and efficient dispersion of the particles for long-term applications. Use of surfactant, non-covalent functionalization of nanoparticles, control pH, and sonication are some primary approaches for increasing the stability of the. Now, nanofluids, as I told earlier, these can be produced by two methods. The first one is the one-step, and the other one is the two-step. In one-step method, the single step simultaneously makes and disperses the nanoparticles directly into the base fluid. Whether both are being done at the same time, the preparation of the nanoparticles and the mixing with the fluid. But in the second two-step method, It's first, in the first case, we produce the nanoparticles and then we disperse them into the fluids. It's a two-step. The first is making and then it's the dispersing. Nanofluids basically are the dilute suspensions of the nanomaterials with distinctive and enhanced features. Stability of nanofluids is the only quantity factor which decreases the efficiency of such smart fluids in engineering applications. This pictorial diagram you can see over here both the nanoparticle preparation and mixing it with the base fluid. This is the one step, and then this is the second preparation of the nanoparticles and then adding it to the base fluids. And with the two step thing, first the making and then adding. The one-step process consists of simultaneously making and dispersing the nanoparticles in it. And in this method, the process of drying, storage, transportation, and dispersion of nanoparticles are divided. So the agglomeration of nanoparticles minimized and stability of the fluid is increased. Now coming to the two-step method. In two-step method, the most widely used for the preparing nanofluids. Now, one-step method, people can say that in experiments or in the labs, it's preferably the two-step method. During the two-step method, the nanomaterials directly are prepared and then they are being added to the. Now, overview of some experiment results you can see. These are the nanoparticles, the base fluid, increase in the thermal conductivity, and the application where are used. You can see ferrous oxide mixed with the water increases the thermal conductivity by 70%, and these are being used in the hybrid power engines. Similarly, the multiple carbon nanotubes adding with the olefin oil increases the thermal conductivity by 160%, and air conditioning is being used in the air conditioning process. Then the titanium oxide, you can see with much water, it increases the thermal conductivity by 30 to 33%, and it is being used in the heat sinks. Then the aluminium oxide mixed with automatic transmission oil increases the, say, the thermal conductivity by 30%, and is in the vehicle. Some overview of experiment results. You can see over here, same that I have told you already, that the nanoparticles, the base fluids, the size of the nanoparticles, the volume fraction. Volume fraction is how much the quantity of the nanoparticles being added into the base fluid, and this is the enhancement, basically the percentage. So, and these are the different experiments which are taken from the papers who has conducted these experiments. Let's say titanium oxide mixed with a giant glycol. Then the size of the nanoparticle used in the experiment is 15, and the volume fraction used as a 5%, and the increase in the let's say that's similar. The rest of them you can see over here how effective the nanofluids are in enhancing the thermal conductivity of the different base fluids. Now the parameters affecting the thermal conductivity of the nanofluids, you can see this particle, the volume fraction, particle size, particle shape, particle material, base fluids, temperature, effect of acidity, that's a pH. All these play a vital role in enhancing affecting the conductivity. If we talk about the volume fraction, we see these graphs over here. The particle volume fraction affect the gauge in water. You can see over here in the body fraction of the Si silicon in the water. 6% of volume fraction of copper oxide and the particle distilled water suspension result in an increase in effective thermal conductivity of 1.52 times that of the pure distilled water, and 10% of aluminum oxide nanoparticle distilled water suspension increased effective thermal conductivity by a factor of 120 at a temperature of around, you can say, the room temperature 34 degrees Celsius. Now, if we talk about the size, the effect of the size, particle size, and the thermal conductivity, the smaller particle has the possess the higher thermal conductivity. Effective surface area increases as particle size decreases. Increment due to Brownian motion, exponential increment of size getting smaller. If we talk about the particle shape, the cylindrical shape and particles extended profile geometry can transport heat rapidly over the significant distance. High aspect ratio nanoparticles may align parallel to the temperature gradient. So you can see over here that the different shapes, you can say the effect of particle shapes over here and presenting by the graph. Then the effect of the temperature. Increment in the temperature reduces the viscosity of the nanofluids, promoting the Brownian motion. Same volume fraction, highest thermal conductivity, highest temperature, let's say from 7 to 10%, the temperature ranges from 28 degrees Celsius to 25 degrees. When we increase the temperature, the Brownian motion increases, and obviously that thermal conductivity. Temperature increment reduces the viscosity of the nanofluid and consistency at 0.4% volume fraction, different thermal conductivity. Now, if we talk about the features, the characteristics that the nanofluid possess, they have the high heat conduction, they have the stability, reduces chance of erosion, and reduces pumping. In case of high conduction, the nanoparticles have a large surface area which allows more heat transfer. The problem of sedimentation is resolved because of the particles are small, they weight less, thus the chances of sedimentation are also less. Nanoparticles are very small, hence the momentum they impart on the solid wall is very small. This reduced momentum reduces the chance of collision of components such as heat exchanger, pipeline, pumps, and these reduce the pumping power. In case of the nanofluid, the required increase in the pumping power. Effect of the Brownian motion. The Brownian motion is the random motion of the particles suspended in the fluid. This random motion transport heat directly to the more Brownian motion. Now the clustering of the nanoparticles, it results in fast heat transport along relatively long distances, since heat can be conducted much faster by solid particles. As here again and again telling that this is basically the dispersion of the metallic particles into the base fluids. Once the particles are inserted into the base fluid, there you can say the conduction will be more faster, because in case of the solid particle is slow as compared to the liquids. Interfacial layer effects around the nanoparticles. Liquids molecules are also known to form the ordered layer structure at solid surfaces, and these interfacial layers have different thermophysical properties from the bulk, liquid, and solid particles. because of order structure of the nanolayer, it has higher thermal conductivity than the bulk. Now, if we talk about the applications, this is hopefully the most interesting type where nanofluids are being used in our daily life. The first is in the solar panels. You can say the shortage of the fossil fuels and environmental considerations motivated the researchers to use alternate energy sources such as the solar energy. Therefore, it is essential to enhance the efficiency of the solar system. So, to enhance the performance of the solar system, nanofluids are widely used. Application nanofluid to the antibacterial activities, antifungal applications. Sometimes of the nanoparticles can be used as the antibacterial activities or drug transmission properties. It is observed that the surface modification of hematite nanoparticles that make them suitable for the antimicrobial applications as well as for other biomedical studies. Despite the continuous improvement of the fungal targeted approaches, a considerable number of therapy associated obstacles, including poor penetration of some drugs and development of drug resistant strains, limit the effectiveness of the fungal therapies. This even growing amount of research demonstrates that a large part of these limitations might be overcome using new nanotechnology-based agents and strategies. Today, to date, a variety of nanomaterials, including biodegradable, polymeric, and copolymeric based structures, metallic nanoparticles, metallic nanocomposites, and lipid-based nanosystems have been thoroughly investigated and presented as innovative antifungal agents. A substantial advancement of nanomaterials focused therapies is the possibility of the administration of these agents through oral, nasal, parental, and intrapolar routes, which are possible due to the small size of the. So these are being used in the medical side as well. Cooling of engine. Nanofluids are also being used in the cooling of engines. One of the innovative technologies used to enhance the heat transfer in the automotive car radiators by using a new type of coolant, which is called the nanocoolant. In few countries, the temperature goes down to below 0 degrees Celsius, wherein nanocoolant, ethylene glycol or glycol family is used as a base load with the nanoparticles because the freezing point of ethylene glycol is minus 12 degrees Celsius. So up to if the temperature is freezing at 0 degrees Celsius, then and we use the ethylene glycol as a base load with the nanoparticles certified, then absolutely the performance of the engine. Industrial cooling, as the thermal conductivity as well as the heat transfer efficient is higher in the nanofluids than the base fluids. It has great application in the industrial cooling process. In one study, a project in 2008 that applied nanofluid for the industrial cooling and result in great energy savings and resulting emissions reductions. For the United States industry, the replacement of cooling and heating water with nanofluids has the potential to conserve 1 trillion BTU of energy. For the United States electric power industry, using nanofluids in closed loop cooling cycles could save about 10 to 30 trillion BTU per year. This is equivalent to the annual energy consumption of about 50,000 to 150,000 households. The associated emission reductions would be approximately 5.6 million metric ton of the carbon dioxide 8,600 metric ton of the nitrogen oxide and 21,000 metric tons of the sulfur. Nanofluids are also being used in aerodynamics cars in looking for the ways to improve the aerodynamics engine, designs of the vehicles, and subsequently the fuel economy. Manufacturers must reduce the amount of energy needed to overcome wind resistance on the road. At high speed, approximately 65% of the total energy output from a truck is expended in overcoming the aerodynamics drag. This fact is partly due to the large radiator in front of the engine position to maximize the cooling effect of the oncoming air. The use of nanofluids as coolants would allow for smaller size and better positioning of the radiators, owing to the fact that there would be less fluid due to higher efficiency. Coolant pumps could be shrunk and truck engines could be operated at high temperatures, allowing for more horsepower while still meeting stating emission standards. Nanofluids are also being used in cooling of the nuclear reactors. Many water-cooled nuclear power systems are CHF limited, but the application of the nanofluid can greatly improve the CHF of the coolants so that there is a bottom line economic benefit, which also raising the safety standard of the power plant systems. Another possible application of the nanofluids in nuclear system is the alleviation of the postulated severe accidents during which the core melts and relocates to the bottom of the reactor vessel. In such accidents were to occur, if such accidents were to occur, it is desirable to retain the molten fuel within the vessel by removing the decay heat through the vessel wall. This process is limited by occurrence of the CHF on the vessel outer surface, but analysis indicates that the use of nanofluid can increase the in-vessel retention capabilities of the nuclear reactors as much by 40%. Cooling of the microchips in the computers. A principal limitation on the developing smaller microchips is the rapid heat dissipation. However, nanofluids can be used for the liquid cooling of the computer processes due to their high thermal. It is predicted that the next generation of the computer chips will produce localized heat flux over 10 megawatt per meter square with total power exceeding 300 watts. In combination with the thin film evaporation, the nanofluid oscillating heat pipe cooling system will be able to remove heat fluxes over 10 megawatt per meter square and serves as the next generation cooling device that will be able to handle the heat dissipating coming from the use of the nanofluids in the defense systems. A number of military devices and systems require high heat flux cooling level of tens of megawatt per meter square. At this level, cooling with conventional fluids is challenging. Examples of military applications include the cooling of power electronics and directed energy weapons. Directed energy weapons involve high heat flux more than 500 to 1000 watt per centimeter square, and providing adequate cooling of them and associated power electronics in a critical need is a critical need. Nanofluids have the potential to provide the required cooling in such application as well as in the other military systems, including military vehicles, submarines, and high-power laser diodes. In some cases, nanofluids reach for defense application includes multifunctional nanofluids with added thermal energy storage or energy harvesting through chemical reaction. Cooling and heating in buildings. Various nanofluids can be applied in conventional heat exchangers used in buildings. Analysis shows that nanofluids applications could result in volumetric flow reduction in the mass flow rate, and pumping power savings. Nanofluids also require smaller heating systems in order to be capable of delivering the same amount of thermal energy, thus reducing the size and initial cost of the equipment. This will reduce the release of pollutants to the environment due to a reduction in power consumption and the waste produced at the end of the heat transfer system's life cycle. In cooling system, nanofluids can be used in place of the chilled water, which is commonly used in coils of air conditioning ducts. Nanofluids in cameras, micro devices, and displays. A new study has demonstrated that the liquids embedded with the nanoparticles show enhanced performance and stability when exposed to electric fields, which could lead to new types of the miniature camera lenses, cell phones, displays, and other microfluidics devices. This study reported that this type of study may open a new vista for using nanofluids in microscale and nanoscale actuated device applications. Application in chillers. Many reported that 40% increase in the thermal conductivity for 0.4% volume fraction of nanofluids. This gives an opportunity for improving performance of the chillers in air conditioning system. Surprisingly, the cooling capacity of the nanofluids could increase by 4.2% at the standard rating conditions. At 6.7% increase in capacity was enhanced at a flow rate of 60 liters per minute. Medical applications. Nanofluids and nanoparticles have many applications in biomedical industry, but there are some side effects in the traditional cancer treatment methods. Iron-based nanoparticles can be used as a delivery vehicle for the drugs or radiation without damaging nearby healthy tissues. Such particles could be guided in the bottom stream to a tumor using magnets external to the body. Nanofluids could also use for safer surgery by producing effective cooling around the surgical region and thereby enhancing the patient's chance of survival and reducing the risk of organ damage. Magnetic nanoparticles in biofluids can be used as the delivery vehicle for drugs or radiation, providing new cancer treatment techniques. Magnetic nanoparticle absorbs much more power than the microparticles as AC magnetic fields tolerable to use. Nanoparticles are more adhesive to the tumor cells than normal cells. Therefore, magnetic nanoparticle excited by, by the AC magnetic field is promising for cancer therapy. There is a new initiative which takes advantage of several properties of the certain nanofluid to use the cancer imaging and drug delivery. This initiative involves the use of iron-based nanoparticles as delivery vehicle for the drugs and radiation cancer particles. Magnetic nanoparticles are used to guide the particles up to the bloodstream, the tumor, and with magnet. It allows doctors to deliver high local doses of drugs or radiation without damaging nearby healthy tissues, which is a significant side effect of the traditional cancer treatment. These are the you can see the results of some studies. You can see the particle being chosen as model that is such type that is the experiment and the photothermal hyperthermia. What are the absorption of 80% Celsius threshold reached this year with These all are basically the medical side, the uses of the particles and electrons. You can see this ferrous oxide, the iron particle that I was talking about in the last slide. This is the search type, that is the Richmond type, the hyperthermia. Two hyperthermia treatments stop tumor growth. So by using of these particles, this is the more safer as compared to non. Now, the challenge is for the making of the nanofluids. The first one, that is, you can say, the high cost of nanofluids. It is marked that despite the amazing performance of the nanoparticles to solve the problems, the high cost of nanofluids utilization always one of the most important reasons that many hinder the application and industry. So gradually the science is developing, and initially you can say, as I told you, that here in the previous slide you said the nano has single wall nanotubes, and the multi-wall ranges from the 50 to $200 per kg. Initially, it was around, you can say, $1,000 per kg, but now with improvement in the science, it has reduced the cost, but is further need to for the making of the nanoparticles. We need further experiments and the development in science so that the cost will further be reduced. The disagreement between the most of the experimental data and the theoretical model predictions. There is the disparity between the theoretical presentation of the studies given by the different authors and the experiment conducted in GSG. Those theoretical work. Experimental work gives approximate, you can say, near to the theoretical work, but not exactly what the theoretical work say. Nanofluids have displayed enormously exciting potential applications. Some vital hinders also exist before commercialization of nanofluids. The following key shows should receive greater attention in the future. Firstly, the further experiment and critical research is required to find the major factors influencing the performance of the nanofluids. Up to now, there is a lack of agreement between the experiment search from the different groups, so it is important to systematically identify both these factors, the trade and accurate structures. Characterization of the suspension may be the key to explain the discrepancies of difficulties in the production process. The manufacturing of the nanofluids has employed either a single step, as I told you here, that simultaneously makes and disperses the nanoparticles in the base fluids, or the two-step approach that involves generating the nanoparticles and subsequently dispersing. Using either of these two approaches, nanoparticles inherently produce from processes that involve reduction, reactions, or ion exchange. Furthermore, the base fluids contain other ions and reaction products that are difficult or impossible to separate from the fluids. Another difficulty encountered in the nanofluid manufacturing is the nanoparticle tendency to agglomerate into larger particles, which limits the benefits of the high surface area. Stability of the nanofluids is one of the key challenges in the widespread practical application of nanofluids. Generally, the long-term stability of the nanoparticle dispersion is one of the basic requirements of the nanofluids application. The stability of the nanofluids has a good corresponding relationship with the enhancement of the conductivity, where the better of the dispersion behavior, the thermal conductivity of the nanofluids. To get stable nanofluids, physical or chemical treatments have been conducted, such as an addition of the surface modification of the suspended particles, or applying strong force on the clusters of the suspended particles. Dispersing agents, surface active agents, have been used to disperse the fine particles, hydrophobic materials in the atmosphere. Thermal conductivity, viscosity, and specific heat models of the nanofluids in the metal. There are so many, let's say, the thermal conductivity for the metal, the viscosity, and specific. There are so many different models are available for literature. The one is confused which model is better and which model is supposed to adopt for the production of nanofluids. There you can say still great opportunities available for nanofluids. As we have discussed in the slide that the production of the nanofluids is relatively high cost, so experiments and more search is needed to make them economical for as far as the production is concerned. Secondly, the production of nanoparticles with more accurate size. Sometimes when we produce the nanoparticles, the sizes of the particles vary. We need to have the same size particles for the efficient, for to enhance the efficiency of the investigation on the environmentally friendly as well as the safe as nanoparticles. Obviously, these are being used in the labs. One has to cater all the measures to be safe as far as the health of the individual is concerned. Determining the thermal conductivity of nanofluids accurately, different studies give different data. Although they are relatively very close, but even then they are not approaching to the one exact figure that the thermal conductivity of this fluid will be this one, this fluid will be this one. There will be a little variation in the thermal conductivity on the different experiments. Research on how to make the nanofluids more stable. Stability of the nanofluids is one of the key factors that the scientists are working on. That once the nanofluids is made, how much time it can be retained, that it can be used in the future. Let's say 1 month, 2 months, 6 months, or 1 year, or 2 years. With the passage of time, the stability problems is there in the nanofluids. So more studies and more experiments are needed in this site. Then the estimation of the effective viscosity of the nanofluids accurately. Again, what I mentioned earlier, that there are variation in the calculating the viscosity, the thermal conductivity of the nanofluids. So the scientists have to be focused on these problems as well. Popularity, you can well imagine. I have already told you about the practical applications of the nanofluids, and this is the area that maximum research is being conducted nowadays since the year its inception. Let's say from the year 2000 onwards. You can well imagine from this chart that from 1996, basically this was the only exception where one paper or two papers were there, but actually it starts from the 2000 in the, let's say, 2004 from onwards. You can see there's the nanofluids in the title and the nanofluid in the article, and you can see the nanofluid in the title as this dark blue line, and the number of articles is approaching to, let's say, around 2300, starting from, let's say, yes, 200 like this one. How rapidly there is a still there's a big margin. This is from data from 1996 to 2010, and if we move further ahead from 2010 to 2019, you can see the number of paper publications in the past decade, that is 3,165. How you can say exponentially the growth is there in the number of papers, and still there is a big room for the improvement in the nanofluids in this area. If I urge the students who are taking this session, that if you are interesting, if you find that in which way you are looking for the area that in which way we have to start the search, I must urge you people to come to this year. This is from the mechanical side, the experimental side of the nanofluids, and if we talk about the physics students, the mathematics students, they can come to in the area of the nanofluids in the theoretical way. And how much the speed and the going of the search articles you can well imagine. This is a similar graph. The growth shown over here, that the number of articles of nanofluids produced number of particles down to the going the high speed. And now scientists are also have given attention to a new breed of the nanofluids, which is what are the hybrid nanofluids? These are basically the composition of the two or more different materials nanoparticles, the nanoprecise and dispersed into the base fluid. Instead of a nanofluid is basically the dispersion of the one nanoparticle, one type of the nanoparticle, the base fluid, but the hybrid means is the more combination of the different nanoparticles in the base fluid. Now, one combination of the nanoparticles give one reading, and the other combination of the nanoparticles in the base group will give another reading. So now this has started a new era in the say the field of the nanofluid, that the performance, and the scientists have proved this one, that the performance of the hybrid nanofluids is comparatively better in comparison to the nanofluids. Nanofluids are what we have discussed, the traits of the nanofluids, that the high thermal conductivity and the maximum surface area and other things. There's the hybrid nanofluids are possessing, are giving the more better results as compared to the nanofluids. Based on the studies, it is concluded that the thermal conductivity of the hybrid nanofluid can be significantly boosted compared with the conventional fluids or nanofluids, and the boost is not linear, but the concentration of different particles. Hybrid nanofluid showed enhanced characteristics of the thermal conductivity in comparison to the conventional nanofluids. Adding hybrid nanoparticles can significantly enhance thermal conductivity of the base fluid. One of the study measured thermal conductivity of silicon oxide with the water and silicon oxide with the ethylene glycol as compared to their value, the silicon and the copper with the water and silicon oxide with the copper with the ethylene glycol. Obtained results show that adding a small amount of silicon oxide nanoparticles leading to less than 2% enhancement in thermal conductivity of the fluid. However, the deep position of the copper nanoparticles on the silicon oxide results is up to 11% and 11.5%. Mean you can say the usage of the hybrid of the copper and the silicon oxide is giving 11.5 and 11% more in comparison to the ordinary nanofluids. So this is all about the presentation and references that are used and take the figures and the graphs from my presentation. Thank you very much. Now, please there. Please, I'm open to the questions. Anything you want to ask, please. Thank you. Lena, are you there, please?
Hello, everyone. Yeah, thank you for Professor Mohammed's attractive and brilliant lecture. I think Professor Mohammed have made some full preparation for this lecture. Let's clap, and thanks a lot again for you. And let's go into the session of question and answer. And all students, if you want to have any question, please put it down on the Q&A session board. Yeah, I think Professor Mohammed will answer you. Okay, Professor Mohammed,
Yes.
have you noticed the question 2 on the board?
Sorry, I cannot see this.
I think.
Can you share the screen with me, your screen?
Okay, I think I can read it. One of the challenges of nanofluids
Nanofluids.
is the disagreement between experimental data and the theoretical prediction. Therefore, how can solve the disagreement?
Yes. Actually, as I told in my presentation, that there is, if you can say, the smaller fluctuation between the results, experiments that are being conducted in the labs and the theoretical work that the scientists are presenting. So these, obviously, this is a challenge that both the experimental and the theoretical results should overlap, and there shouldn't be any discrepancies between the results. But I have included this thing in the challenges as well, that this is the challenge that we are facing, that there is a difference between the you can say the experiment work and the theoretical work, but the search is going on day by day, is improving, and we are expecting that with the passage of time that both this discrepancy or the gap between the experimental and the theoretical set will be squeezed gradually.
Thank you, Dr. Mohammed. This is Lan. I sent you the message through the WeChat. You can access the Q&A part on the left of the chat at the bottom of your Zoom presentation. So when the student sends the question, yeah,
now
you can.
see.
Yeah, that's great.
Okay. Any other question? What was the question that is being dispensed by the ILO? I have answered this question, that there is the discrepancy between the experiment. D as the science is growing day by day with the passage of time. Hopefully, this gap between the experiment and theoretical is squeezed, and it will be narrowed down, and ultimately it will come to one. And then there will be no overlapping, there will be no gap between the experiment and the theoretical. Yes, please, next. Any further question, Lynn? Can you hear me?
Okay, any question? I noticed one student raised this question. Thank you for your nice presentation and explanation. It's a very important topic. Could you give us the document, please? I mean, maybe these students maybe want your PPT and or transfer it to PDF edition. I think it depends on you, Professor.
Are you giving me some more questions, or should I stop now? Sorry, I don't get your voice.
Yeah, I think one student raised a question. If you would like to share your PowerPoint of this topic or transfer it into PDF edition.
Yes, I will. I will transfer this one in the PDF and will send to the link, and she can upload to into the, let's say, the.
Okay, that's great. Yeah, I think Professor Muhammad, I think you can give the addition to Dr. Lan Liu through WeChat, and she will send this document or this PDF edition to the students who raised the question named Elinu Ayali. Okay, thank you very much.
Thank you very much. Stay blessed. Thank you.
Okay.
Thank you, Dr. Muhammad.
Thank you.